Welcome all of you to the 14th session of research discussion on graphs and groups. May I request Professor Ambat Vijay Kumar to introduce the speaker.
Good evening, all of you. I have great pleasure to introduce Scott Harper from the School of Mathematics, University of Bristol. He is a PhD in mathematics from University of Bristol on his thesis on the spread of classical groups. And he is also he did masters from University of St. Andrews, and he has quite very good number of exciting publications in very reputed journals like Annals of Mathematics, Algebraic Combinatorics, and Bulletin of London Mathematical Society. He has received several distinctions and awards, the most recent being Gold Medal in Mathematical Sciences at STEM for Britain, and Faculty of Science Commendation awarded for an outstanding PhD thesis. He has given a lot of invited talks and organized several programs, also seminars and conferences. With this introduction, I invite Scott Harper to give his lecture on generating graphs, spread, and domination. Scott,
thank you very much. Thank you very much for that very kind introduction. I'm just going to share my screen so you can see my notes. It's a real pleasure to be speaking at this research discussion series. Graphs and groups are two very interesting aspects of mathematics, and their combination is something I'm very interested in. So I'm keen to be speaking to you all today. So I want to be talking about a particular group that you can associate, a particular graph that you can associate to a group called the generating graph, which I'm sure people in this audience will have encountered before, but I'll soon define it. And I want to talk about recent work on invariants that measure how connected this graph is for particular families of interesting groups. So let me just begin by just defining the generating graph. So for this talk, I'm going to be considering only finite groups, though the theory is also interesting for infinite ones, but that's not the focus here. So let G be a finite group. And I'm now going to define the generating graph. So the generating graph of G, so I'll denote that gamma of G. And this is what some people might call the reduced generating graph, but I'll just call it the generating graph. And it has vertices as the non-trivial elements of the group. So here one is the trivial group, and the edges are the generating pairs. Or said otherwise, two elements of the group will be adjacent by an edge exactly when they generate the group. So clearly this is just an interesting graph for two generated groups, but fortunately our broad and rich class of finite groups can be generated by two elements. So as you can see, I've got a couple of three pictures on the screen, two at the moment. One is the generating graph of the dihedral group, generated by an element A of order 4 and B of order 2. And you can see that there are various edges. It'd be an easy exercise to construct this graph yourself. The interesting thing, I guess, is the fact that there is an element, a vertex, that's not adjacent to anything. It's an isolated vertex. And in this case, it's the element of order 2 that generates the center of the group. It commutes with everything and generates with nothing. So that's one example of a generating graph. Another one is of the alternating group A4. And here you can see that there are numerous edges and the graph is connected. And in fact, the only edges that are missing are that edge, that edge, that edge, that edge. So the only edges that are missing are the edges corresponding to these proper subgroups, the 4 of them of order 3 and 1 of them of order 4. So in this case, yeah, it's very connected. There are lots of edges. The final example is a graph I very much like the picture of. and it's the generating graph of the alternating group A5, the smallest non-abelian simple group. And I've arranged the dots of the elements, the vertices, and I've arranged them in the 3 concentric circles corresponding to the orders of the elements. So the elements on the outside ring are the elements of order 2, and any 2 elements of order 2 will generate a dihedral group, so they won't generate the whole group, and consequently are not, in any case, adjacent. So you can see there are many edges, far too many to make out in the picture, but certainly also several non-edges. Nonetheless, this group is connected, and it looks, by a first glance, very connected. Okay, so I now want to start making precise what very connected and isolated vertex really ought to mean. So let me begin by doing that properly. So I want to really just cut to the chase, I guess, and just tell you what we know about the connectedness of the generating graphs of finite groups. So the connectedness of gamma of G. So here's the main theorem, and I'll just tell you it. So it's a theorem of Tim Burness, who's also in Bristol, Robert Goralnik in the USA, and me, published this year. And it asserts that the following conditions are equivalent. So the following are equivalent. So in attempting to answer the question of how connected are generating graphs, or when are they connected. So the following 3 things are equivalent. Number 1, the graph has no isolated vertices. Right, so if this is a very, I guess, weak connectedness condition, right? Because we're saying that there's no isolated vertices excludes the possibility of there being connected components of size just 1. Okay, but in fact, that's actually equivalent to the stronger property that the graph is connected. So certainly, if the graph's connected, there are no isolated vertices, but unless the graph has size 1. But in this case, obviously it's stronger in general, and it's actually implied by it. And the third condition is that the graph has diameter 2. So this is, I guess, one of the main bits of content from this theorem is that these 3 conditions, seemingly increasing in strength, are actually equivalent for generating graphs. As soon as you have no isolated vertices, you are connected with diameter 2. Or diameter at most 2, I guess I should say. And moreover, we can answer the question of when does a finite group have a generating graph with these 3 equivalent properties? And the answer is a straightforward group theoretic condition. And it's the following, that whenever you take a quotient of the group that's not the whole group, it ought to be cyclic. So G by N is cyclic for all non-trivial quotients, or for, all proper quotients, for quotients by all non-trivial normal subgroups. So as I said, these 2 conditions, these 2 implications are immediate, and this condition here is actually also straightforward, and I'll explain why that's true in a minute. But before I do so, let me just remark on the history of this problem. So we proved this year, but various aspects of this had been asked many years before. So the question of how are these conditions related, are these 3 connectedness conditions equivalent, was in other language asked about 50 years ago by Brenner and Viegold, who in some sense began the work on this topic. So they didn't conjecture this, but they asked a question that amounts to saying, for which groups do we have there being no isolated vertices, but not the stronger condition of having diameter 2? So what groups are kind of in that gap? And they conjectured maybe there were only finitely many that had that property, and we now know there are none. So that's kind of that question's been floating around for a while. The question of which groups, which groups have any of these properties, what's the group theoretic condition, that was conjectured by Breuer, Guralnik, and Cantor in 2008. So about just over a decade old as a conjecture, which we've now solved. So this theorem, solves a number of questions that have been around for a while. So I'm not going to say a huge amount about the proof of this theorem. I'm going to dig into a very specific aspect of it for most of the talk. But let me just say a couple of things. So let me first begin by just indicating why this implication that I said was straightforward is indeed straightforward. So why does 1 imply 0? So let's see. We assume 1, right? We assume 1, and and you also note that this bit doesn't rely on the group being finite, but lots of the other things I will soon say do. So we assume that the group has no isolated vertices, and we take a non-trivial normal subgroup, and we want to show the quotient by that is cyclic. So we take some non-trivial element of that normal subgroup. Sorry, non-trivial element of that normal subgroup, and we note that because of 1, that's a vertex in my generating graph, and condition 1 promises me that there ought to be another vertex that's adjacent to it, otherwise it'd be isolated. So I'm saying that there must be a vertex, an element G, such that the group G is generated by G and N. But now if we look at the quotient, we see that the quotient must be generated by the cosets NG and NN, but NN is just the identity. So this is a cyclic group, and we're done. So 1 does indeed imply 0. If there are no isolated vertices, then all proper quotients of the group are cyclic. So the main bit of work that was done in proving this theorem, I guess, was proving that 0 implies 3. So need to prove that 0 implies 3. And so we're proving that for a particular class of groups, the groups that satisfy 0, that they all have this graph theoretic property 3. So I'll tell you the 3 steps in proving this, and then I'll say very little more. So the last thing to be done, but in some sense theoretically the first thing to do, is to reduce this problem to, instead of being about all finite groups, which the hypothesis of the theorem essentially is, instead of being about all finite groups, you reduce it to a class of groups, to the almost simple groups. And I'm not going to say what the almost simple groups are, because they're not going to feature later, but there are, if you don't know, there are a class of finite groups that includes the simple groups and closely related groups. So for example, as well as including AN, the alternating group, it includes SN, the symmetric group. So this was one of the 2 things that we did in our paper this year. So it's BGH. And that was quite an appealing thing to do, because historically the first step in this process was to prove the result for the simple groups. So the simple groups certainly have the property that all proper quotients are cyclic, because all proper quotients of a simple group are trivial. So this was always going to be a case that would have to be handled, and it was handled using kind of really introducing lots of nice new ideas by Guralnik and Cantor, and later Thomas Breuer also. So Breuer, Guralnik, and Cantor, I'll just say in 2008. So the big gap between these 2 points in the 3-point plan is to say we've reduced the problem to almost simple groups, and we've done it for simple groups. So we just have to extend the work on simple groups to almost simple groups. And okay, I haven't told you what almost simple groups are, but the name would suggest that there really isn't very much to do there, right? That if it's known for simple groups, how much harder can it be to do it for the almost simple groups? unfortunately, that's just actually not the case. And indeed, the vast majority of pages of this proof are dedicated to the extension from simple groups to almost simple groups. And I guess the small piece of intuition of why is because it's not really an extension at all. It's completely new, and it's the one thing that makes an almost simple group different from a simple group, this addition of an extra automorphism, is exactly the thing you need to focus on in the proof. You can't brush it under the carpet like you can in some problems. It's the focus of the problem. So let me just say that there was a huge amount of work that went into proving this for almost simple groups. And I'll just say by who. So we, in our most recent paper, handled the exceptional groups of Lie type in a monograph, and another paper, I handled the classical groups of Lie type, and was also initial work on the classical groups of Lie type by Tim Burness and Simon Guest. And the one phrase, two-word answer of how we did this step was exploiting a technique that I won't say anything about called Shintani descent. But the development of this theory is the crucial ingredient. It's really the subject of a different talk. So anyway, so that was just to tell you who's been involved in proving this theorem. For most of the talk, I want to really focus on the simple groups. And I want to talk more about the graph theoretic properties of the generating graphs of simple groups. But before I do that, let me just make one final comment on this theorem. Because as I've stated it's just a theorem about generating graphs, and therefore about groups that can be generated by two elements. And you might ask if similar sorts of things are true for other groups that require 10 generators or 42 generators. And the answer is that it is true. So let me just rephrase this theorem, or part of this theorem, in a way that applies to all finite groups in a slightly stronger way. So here's a theorem. So I'll rephrase part of our theorem first, and then I'll edit it. So this is just a rephrasing of part of 0 is if and only if 1 in the theorem above. So every non-trivial element of G is contained in a generating pair, or generating set of size 2. Right, that's condition 1. If and only if every proper quotient of G requires just one generator. So that's kind of focusing on groups that are two generated. But actually, for groups that are 3, 4, 5, 6 generated, this was already known by work of Cristina Acciari and Andrea Lucchini a couple of years earlier. And so let me just edit this theorem. Every non-trivial element of G is contained in a, let's say, generating set of minimal size, if and only if every proper quotient of G requires strictly fewer generators than the original group. So if you have a group that whose minimal generating set has size 42, then every non-trivial element of the group is in fact contained in a generating set of size 42, if and only if every quotient of the group, that's not the whole group, requires at most 41 generators. So we proved the case for 2 generators, which is somehow different and harder, but in fact every other number was already known a few years earlier. So that's what I wanted to say by way of a bit of a remark. But now I want to turn to this word that was in the title of the talk, domination, and focus on simple groups, where I think, it's a bit more graph theoretic. So let me begin by just recalling a result and a definition. So domination of the generating graph. Before I do move on, are there any kind of burning questions about what I've just said before I change gear? I'll take that to be no. Yes.
What happens to the elements of the Fratini subgroup in these things? I mean, they're non-generators, right? So if you have a non-cyclic group, then they become isolated.
That's right.
So in the setting that you have of equivalent conditions, then it also means that they will have trivial Fratini subgroup. Is that right? If it's more than 2 generated.
Exactly. So if you're more than two generated, then I guess this theorem at the bottom is implying that if you have a non-trivial Fratini subgroup, then you must have a quotient that requires the same number of generators as a whole group.
Right. Okay.
Exactly.
Right. Yeah. Thanks.
You're welcome. So so now we're going to turn to talk about domination. So as I say, the focus is going to be on non-abelian finite simple groups. So G is a non-abelian finite simple group. These are somehow the stars of the first theorem, so it'd be nice just to focus on them now. So let me just recall what we know. So the step that I mentioned above, I said it was done by, I guess, originally by Goralnik and Cantor, and what they said was the generating graph for these groups has no isolated vertices. And just to say that explicitly, that's saying that for any non-trivial element of the group, there is some element of the group that is connected to it. Right, that's what it means for there not to be any isolated vertices. So you could ask the question of, well, what about this there exists, right? So what do we know about this element Y? You give me an element X, and this theorem assures me that out there somewhere is an element Y that generates with it. The question is, how do you find that element Y? Well, they partially answer that question. They actually say, in fact, you can fix a conjugacy class C such that for any non-trivial element of the group, writing the same thing as above, there's something in that specific conjugacy class that generates with your element, that's connected to your element. So this raises the question of, well, okay, what class is it? Well, it turns out it's quite a large class. It's a very large class, typically. So you might ask, well, can you get away with not using the whole class, but maybe just some proper subset of that class, or some other small subset of the group? And this motivates the idea of studying domination or total domination numbers of the generating graph. So let me just recall the group theoretic notion, so the graph theoretic notion. So a subset of the vertex set of a graph is a total dominating set if every vertex is adjacent to something in that set. So if for all vertices of the graph, there is an element, or there's a vertex Y in that set that's adjacent to it. So everything's adjacent to something in this set. I'll draw a picture in a minute that will hopefully be useful. And as I just said above, it's natural to try to find as small a set as possible, right? Because obviously you could just take, I guess you could take the whole graph, right? If there were no isolated vertices. So you may as well want to find the smallest possible set. So, and that's called the total domination number. So the total domination number of the graph gamma, which we write as lower, there's a kind of T in the subscript for total, the total domination number, gamma T of gamma, different gamma, is the least size of a TDS, total dominating set. TDS. Great. So let's just look at a picture. This is the generating graph of the alternating group A4 again. And you can see I've highlighted two vertices in red. And you look at all their neighbors, which are marked by kind of red edges. You can see that between them, every element is adjacent to one of those two. So that is a total dominating set. So in red, that is a total dominating set of gamma of A4. And in fact, you're never going to just be able to find a total dominating set of size 1, because the definition would actually force that element to be adjacent to itself. Every element, including itself, is adjacent to it. And that's impossible. I mean, this graph has no loops and will be impossible in all non-cyclic groups. So the total domination number is at least 2. And in fact, it's exactly 2 in this case. So the total domination number of A4 is 2. And I've deliberately abused notation because I'm going to do it for the rest of the talk. I'm always going to write the domination number of the group rather than the graph of the group, just to ease notation slightly. So the question is, well, can you always find, so I know this is not a simple group, but simple groups are just too big to draw. The question for finite simple groups, can you always find a total dominating set of size 2, for example? Or if not, how small, and so on. So that's the main focus for the rest of this talk. So let me begin by just giving another example, an example that actually pertains to finite simple groups this time. So the example is as follows. I've got a group G, which is an alternating group of prime degree. So it's AP, where P is at least 13 and prime. Just small, unusual things happen with small, unusual groups. So let's just assume that P is at least 13. Then, well, I can give you an example of a total dominating set, the one that you'd get from Gralnick and Cantor's theorem, which is the set of all P cycle, that conjugacy class, which I guess is half of the P cycles. So this is a total dominating set. So everything in the graph is adjacent to something in that class, that conjugacy class. But you don't need all of that class, which is huge, right? It's a fraction 1 over P of the whole group. In fact, you only need 2 of the P cycles. So let me say that. In fact, the total domination number of AP is just 2. So I'll give you an example. If P is 13, then I can write down 2 P cycles that work. So one P cycle will just be 1 up to 13. And the other P cycle is 1 up to 8. And then I put the last few in a slightly different order, 13, 12, 10, 9, 11. It turns out, and you can check on a computer, that any element will generate with one of those 2. Every vertex is adjacent to one of those 2 vertices. And what's even more striking is if we say P is at least more than 13, then if I just randomly choose 2 elements from this conjugacy class, then this will be a total dominating set with probability at least 1 minus 1 over P. So with probability that tends towards 1 with P, if you just randomly choose 2 elements in that set, they'll work. So this is, I think, really quite surprising. Not only can you find a total dominating set of theoretically smallest possible size, but just randomly searching in appropriate conjugacy classes, we'll find you one.
Sorry. Are these, in the case of 13, are these 2 adjacent?
Are these 2 adjacent?
As in the case of A4?
I think so. Let me just. Yes, I think they are. I think
in that case, my concern is, can you find 2 such that they are not adjacent. Are they independent total dominating sets? They are supposed to be called perfect dominating sets.
Okay, so that's really interesting.
Yeah.
That's a good question. I'm not going to answer it on the spot because I won't be able to answer.
I think
since
for
you are selecting
total
arbitrarily
dominating
two,
sets, no, for total dominating sets of size 2, I mean, they cannot be independent. They has to be adjacent to each other. Otherwise, one will not dominate the other. If we have a total dominating set of size 2,
yes.
so there has to be adjacent.
Yes, you are correct.
Yes.
You are correct. Yeah.
You're absolutely right. Thank you very much.
Okay, fine.
Everything generates with one of the two. It can't generate with itself, so it has to generate with the other one. Exactly.
Of course, in the total dominating, that x not equal to y must be there. That is why there exists a y such that x not equal to y. Okay.
Yes.
Yeah. Okay. Here, somewhere else you put it. There exists a y that is not equal to.
No, I think so. So I'll apologize if I've misused the terminology, but for the purpose of this talk, I definitely want y to be allowed to be x. So
fine.
I'll just reiterate that. So S is a total dominating set, at least for the purpose of this talk, if given anything in any vertex, there is a vertex possibly equal in that set that generates with it, adjacent to it. Okay, so we've seen this example with the alternating groups of prime degree. So let me now just zoom out slightly and just tell you something about all finite simple groups, and not just the alternating groups of prime degree. So I guess this is our main result on this topic. So here we go. This is a result of Tim Burness and me from 29 across two different papers, one from 2019 and one from 2020. And the first statement is it's not particularly satisfying, but just the way it's phrased. There are infinitely many. So we're in the land of finite simple groups, right? So there are infinitely many finite simple groups G with total domination number 2. So let me just give you some examples. We've already seen that this theorem is true, right? Because AP of P prime is certain. But let me give you some other examples. PSLNQ, where n at least 3 is odd. E8Q for any Q, the exceptional group of Lie type. The monster group, the largest sporadic simple group, they're all examples where you can find a total domination total dominating set of size 2. And in fact, we have almost classified the finite simple groups that have this property. So let me just say there's a near classification. I'll explain what I mean by that in a minute. Of G such that gamma T of G is 2. Right. So in a sense, essentially we have classified it, except there are a few cases that we can't settle. And by a few, I mean infinitely many. So I'll give that caveat in a minute. Let me just give one example. The total domination number of an alternating group is 2 if and only if it's what we saw above. It's a prime at least 13. So if you're not prime at least 13, then you don't have a total domination number of size 2, or of 2. So what are just the caveats, just so I can be totally upfront with you. And I guess I'm saying this not just out of transparency, but also as a bit of a challenge. You might want to try to resolve these cases. Symplectic groups of odd rank at least 5 and odd characteristic. We don't know what happens there. Orthogonal groups of even plus or minus of even rank at even dimension, at least 4. And there's 4 specific sporadic groups that we can't handle. I can't remember which groups exactly off the top of my head, but this is in our paper, the second of the 2 papers. So if you wanted to try to resolve those little cases, you could, but we couldn't. So that's that. And let me just say, what happens when it's not 2? How big can it be? Well, actually, it can be as big as you'd like. So in general, the total domination number of a finite simple group is unbounded. So let me just give an example of that. Again, in the context of alternating groups, the total domination number of the alternating group AN is always at least log Pn, where P is the least prime divisor of N. So for example, if N is even, then the total domination number has to be at least log base 2 of N. But if P is prime, then this doesn't say much. And indeed, we know the total domination number in that case is 2. So that's kind of what we know. In some sense, we have got the full picture, really, of the total domination number of simple groups. And I want to say a little bit about how we proved this. I just want to highlight one technique because it draws a connection with another area of mathematics, another area of group theory that is very appealing, namely the idea of bases of a permutation group. So for this page, I'll maybe stop my assumption that G is a simple group and just assume it's any finite group acting faithfully on some set omega. And many of you will know this, but let me just tell you what a base for this action is, in case you haven't seen it. So a base is some subset of the set you're acting on. So such a set is a base if, what's the condition? The pointwise stabilizer of the set of the base is trivial. So let me just say that. The pointwise stabilizer, so that's all the G and G that fix every single point of the set. That should be trivial. And let me just give the motivating example. So the motivating example is if you have the group being the group of all invertible matrices on some vector space, then it acts on the non-zero vectors in a faithful way. And a basis of the vector space is a base for this action. And in fact, it has minimal size, minimal possible size. Right, so because if you fix every vector in a basis, then you have to be the identity, right? Then there's no other linear maps that can do that. And moreover, in general, right, the action of a linear map is determined on a basis. That's why we can write them as matrices. So in the same way, the action of a permutation group is determined by its action on a base. It might not, yeah, it's determines action on a base. So for that reason, it's bases provide quite an efficient way of storing how a permutation acts, and therefore they're relevant in in computational group theory. And as I kind of suggested, this minimal size, so it'd be the dimension of a vector space, this minimal size is interesting, and it's called the base size. So the base size, which I'll call BG omega, to keep track of the group and the set, is the minimal size of a base for the action of G on omega. Base size. And unfortunately, I just don't have the time to say everything I'd love to say, or indeed anything I'd love to say about bases. But let me just suffice to say this has been a classical and well-studied topic for many decades, and in recent decades has been really reinvigorated by some quite impressive conjectures that have recently been solved on base size. And Peter Cameron's in the audience. I'll mention at least his conjecture with Cantor, and then his refinement of that kind of asserts that for lots of almost simple groups acting in primitive ways, the base size is very small, usually at most 6. So the point is that the techniques that have been developed to prove these large, really quite important conjectures in recent years have led to techniques that have been useful in lots of other areas, And indeed, nearly every result I've mentioned in this talk uses those sorts of results, those sorts of techniques. But let me go straight on just to saying why I'm talking about bases now, because it has a relationship with domination. Domination and bases. So here's the connection. I'm going to introduce a small piece of notation. So MGS is the set of all M's for maximal, all the maximal subgroups of G that contain S. All the maximal subgroups of G that contain S. So here's the connection lemma. Suppose that I can find some element S that's contained in a unique maximal subgroup. Right, so the only maximal subgroup that contains it is just something called H. And I've kind of forgotten if I'm assuming that G's simple at the moment. It doesn't have to be. So let me just say, and let's assume that H is core free. So this would be kind of guaranteed if H was simple, but let's assume that it's a core free subgroup. So the action on the cosets is faithful. Then here's the connection. We're looking for total dominating sets. Well, this collection of conjugates, so a collection of C conjugates of the element S, that will be a total dominating set if and only if the following condition holds. Which elements don't generate with S, or are not adjacent to S in the generating graph? Well, it's exactly these. Well, the elements in H are exactly the elements that don't generate with S. So if I want everything to be adjacent to one of these C conjugates, one of these conjugates, then I can't have anything in the following intersection. This intersection is all the elements that would be not adjacent to any of those C conjugates. So I need that to be trivial. And for people who know about bases, this condition is exactly saying that these cosets base, or form a base, is a base for the action of G on the right cosets of H. So if G acts on the right cosets of H, this is a base exactly when this is a total dominating set. So anyway, long story short, if you kind of got slightly lost in those details, long story short is, in particular, the total domination number of G is at most the base size of G in the action on the cosets of H. So let me just say that one more time. If I have a group with an element contained in a unique maximal subgroup, which is core free, then the total domination number of the group is at most the base size on the actions on the cosets of that subgroup. So this provides a strong connection between domination and base size. As I said, base size has been studied extensively recently. We can now steal some of those results, but also, where we can't apply this lemma, steal the techniques that were used and apply them to our problem. So in doing that, that's essentially how we proved the theorem that I mentioned above. So somehow, when I'm saying that lots of groups have total domination number 2, that's not unrelated to the statement that lots of primitive actions of simple groups have base size 2. Anyway, I now just want to kind of finish off by connecting together the two things I've said in this talk. So I'm going to scroll back up again. Might be getting a bit seasick. At the start, I mentioned this theorem that had kind of 3 levels of detail. I'll just focus on these 2. And I've really just focused on this. When I went on to domination, I was just talking about isolated vertices, really. When is something adjacent to something else? And I want to see if I can push this up to talk about diameter 2. So I'm going to essentially try to combine the diameter 2 section of this part of the talk with the domination bit that came later. So let me make that precise. So I'll call this going further. So recall, having no isolated vertices means for anything in the graph, there's another thing in the graph that's adjacent to it. Let me write it like this. G is adjacent to H. And that motivated the definition of the total domination number, which is the smallest size of a set S such that this holds for all G and G, and gamma, sorry, there exists some H in the set such that the same picture holds. It's adjacent to it. Having diameter at most 2, let me just say it, 2, is saying for any G1 and G2 in the graph, there is some H in the graph that joins the two of them, kind of provides a path between them. Or maybe sorry, let me draw it a slightly different way. G1, G2, there's something that's adjacent to both of them. And that therefore might inspire the following notion. Gamma 2 of, let's call it the second domination number, is the smallest size of a set that does this. Size of a set S such that for all G1 and G2 in the graph, there's something in the set that does this picture. So the smallest size of a set, so that given any 2 elements, there's something in that set that's adjacent to both. And there, of course, I could just make the general definition. So this is the definition of spread, which I promised to mention in the title. So the spread is just how far you can keep going with this. It's the greatest k such that for all G1 up to Gk in the graph, there's something H, sorry, let me write it here. There's something H that is connected to all k of them. And that should inspire a kth domination number, which is the following. It's the smallest size of a set S such that, I'm just copying the definition from above, for all G1 up to Gk in the graph, sorry, too many different symbols, there is some H in my set that satisfies this picture. So let me just say that all again. The kth domination number of a graph, oh sorry, I've been saying G in all these cases. All these G should be gammas. Sorry, I won't go back and fix them. Is the smallest size of a set, so that for any k vertices, there's some element in my set H that's adjacent to all k of them. And the question is, what can I say about that? I said something about the first domination number. What about the kth domination number? Well, let me at least just focus on the case where we have this maximal subgroup trick we can play. So if G is a non-cyclic group, and I'm supposing that I've got this property, which we don't always have, but I can find an element in a unique maximal subgroup that's core-free, then remember a second ago, right at the start, I said that that means the domination number has to be at least 2 because it's not cyclic. So there are no loops. And I said that the domination number is 2 if I can find if this base size is 2. Right, that was what I said a second ago. I'm now going to say something for the kth domination number. Moreover, the kth domination number is at least k plus 1, and it is k plus 1 if, and I want to fill in this blank. So in the last couple of minutes of this talk, I'm going to fill in that blank. What is the base size information that needs to go there in order to complete the sentence? So I need to introduce a final graph. I'm going to finish with a graph. It's called the Saxo Graph. So this was introduced by Michael Giudice and Tim Burness a couple of years ago, and is named after Jan Saxo and his project for trying to classify the primitive groups with base size 2. So what's the definition? Well, G is a finite group acting, as usual, faithfully on a set omega. Then the Saxo graph, which is written sigma for Saxo, of G omega, captures bases in the same way that the generating graph captures generating sets. So the vertices are the points in the permutation domain, and the edges are the bases. So 2 points are adjacent if they are a base for the action. So now I can tell you what the blank should be. It's a piece of information about the Saxo graph. It is that the Saxo graph has, for this action, has a clique of size k plus 1. So notice that it works. The first row really is the case k equals 1. The first domination number is at least 1 plus 1, which is 2. And it is 2 if the Saxo graph has an edge, right? If it has a k plus 1 clique, a 1 plus 1 clique. That's saying that there is a base of size 2. So the base size is 2. And this now is up to looking at cliques in the Saxo graph. So we used that observation and generalizing all the techniques in the cases we couldn't apply the lemma to answer the question that I suggested a second ago. And it's as follows. Let G be a simple group. And remember earlier in the talk, I had to make some exceptions where we didn't really know what was going on. So I'm going to make those same exceptions again. So infinitely many, but small, but not these groups. So in that case, we have this interesting fact that if the total domination number is 2, then the second total domination number is 3. So we've said already that it's not just the case that given anything, there's something adjacent to it, but given any two things, there's something adjacent to both. And if that thing on the right-hand side can always be chosen from a set of size 2 in the first case, it can be chosen from a set of size 2 in the second case as well. And this is related to the fact, so that somehow suggests that whenever you have a non-empty Saxo graph, you actually have a Saxo graph with a triangle in it. That's maybe suggestive of what I've just said. And indeed, that's a conjecture. So let me conclude with this conjecture of Burness and Giudice, who introduced this graph in a paper that seems to have been published last year. So let G be any finite group, I'm not assuming it's simple, any finite group acting primitively on a set, and assume that it has a base of size 2. Then any two vertices in the Saxo graph have a common neighbor, is the conjecture. So in particular, it would suggest, it would imply that the Saxo graph always has a triangle. If it's non-empty, it has a triangle, which, as I say, is the sort of phenomenon that's suggested by what's right at the top of the screen at the moment, and what we use to prove this result about domination numbers. So that's essentially where I wanted to stop on this kind of journey of studying the graphs associated to generating sets for finite groups. Thanks very much.
Forum is now open for discussion. Any questions or comments?
Excuse me, in your definition of spread, do you say anything more about the points G1, G2, etc., GK the subgraph induced by G1, G2, etc., Gk, no structure is demanded. There exist points, that's all.
I didn't quite follow the question. The definition is that for any k vertices of the graph, there's something that is adjacent to each of them. So you're right, the graph induced by the k vertices has to have a diameter 2. Is that what you just, yeah, that's exactly the definition. And it's not that, sorry, it's not that at all. What is it? But yeah, it's just a case. Given any k vertices, there is another vertex elsewhere in the graph that is connected to all k of them. But in the case where k is 2, you're just saying the graph has diameter 2.
So all you want is G1 is adjacent to H, etc., Gk is adjacent to H, and you are not worried about what is happening inside G1, G2, etc., Gk, isn't it?
Oh, sorry, so it's not clear at all. Let me write it properly. I realised that's not very clear. The greatest case such for all G1 up to Gk, there exists case such that G1 is adjacent to H, G2 is adjacent to H. For also, I'll write it properly. Gi is adjacent to H for all I. So I do care about G2, G3, G4, G5 up to Gk.
No, I think his question is like, what is happening between the vertices G1, G2, Gk?
Yes.
Sorry.
Nothing is said about that.
Yeah, nothing
Can be
said
anything.
They could be adjacent.
Yeah.
They
They could be adjacent or not adjacent.
Exactly.
And similarly, in the previous case, diameter 2 case, could H be equal to G1 or G2?
Yeah, H could be G1 or G2, and G1 or G2 might be adjacent. So I guess strictly speaking, it's diameter at most 2.
At most 2, yeah. In that case, it could be adjacent, right? H could be
Be
either
adjacent.
Yeah.
Have you think about anything regarding domination instead of total domination?
So not particularly. So the total domination, I think we chose that definition just so it matched up neatly with the notion of bases and things.
Yeah. Okay.
We haven't deliberately excluded it, but we haven't thought about it.
But incidentally, that happens to be true in the case of Cayley graphs also. The same situation, the cosets they create a total dominating set. Yeah, at least in some classes of Cayley graphs.
That's really interesting. Thank you.
So Scott, what you were saying earlier, the k vertices, the greatest k such that so the induced graph here will have diameter at most 2, right?
No, so yes, I shouldn't have said that. The graph induced by the G's and the H, I guess. Will
it will have at most 2 diameter.
That will have diameter at most 2, exactly.
Can you just show the part where you had written the lemma which connected the base, the Saxo, this one.
That's it. Yep.
So now you the result that you wrote after this, which was that if gamma, no, the one after this, this thing, because these are not if and only if. I was just wondering whether this theorem had any implication towards the conjecture which you wrote down after this.
So it's the other way around. The conjecture would be useful to prove this lemma, to prove the theorem.
Yeah, but not the other way around, right?
Exactly. Exactly. If the conjecture had been a theorem, this theorem of ours would have been much quicker to prove. It wouldn't have immediately implied it, but in the cases where we have this element contained in a unique maximal subgroup, it would have been an immediate implication, because as soon as you have a non-empty Saxo graph, you get a triangle. So as soon as you have domination number, first domination number being 2, you get the second domination number being 3.
So there's no going the other way in the lemma.
There's no going the other way in the lemma, but actually to prove this theorem, we did have to prove one special case of the conjecture that wasn't yet known. But no, it doesn't imply the other way around.
And what are the kind of examples that you have for when an element is contained in a unique maximal subgroup?
Yeah, so I can write down one example just that is quite indicative. So if you have an alternating group, let's call A2M, so call that G, and I'll take S to be 1 up to K, K plus 1 up to 2M, and K is going to be either M minus 1 or M minus 2, whichever is odd. Then this is contained in a unique maximal subgroup, namely the intransitive one, SK cross S 2M minus K intersected with the alternating group. So that's an example of a simple group with an element contained in a unique maximal subgroup. And that's the sort of thing, that's the sort of trick we would apply also for, say, the general linear group. You try to find, or a classical group in general, you try to find maybe an element that acts irreducibly on 2 big subspaces, and then the only maximal overgroup might be a reducible subgroup. But no, there's an example.
Thank you.
Yeah.
Great.
And actually, I had this only one question over here. You claim it has a triangle, means like, is it like just, I'm not really clear about this has a triangle part.
Oh, I just mean in particular, the Saxo graph has 3 vertices, any 2 of which are adjacent.
Yeah. So is it like, I mean, I was trying to extend it. Can we see that this Saxo graph could be triangulated in a bigger sense, or not necessarily?
So no, I think it does all. I think it implies that every vertex is contained in a triangle, certainly.
Yeah.
Any 2 vertices,
or a C4, I guess. Maybe a triangle or a C4, that any 2 vertices have a common neighbor. Good.
Exactly. So
can we say that, like, can we make an extension to the whole graph is what I'm trying to see.
Yeah. That's a good question. I don't know. I can't think of the top of my head. There's a very convenient thing about Saxo graphs is that because the idea was introduced by Tim Burness and Michael Giudice quite recently, their first paper on it has a wealth of information all in the same place. So you might want to look at their paper and just see if they make these remarks. But I can't think of the top of my head.
Sure. Yeah, thank you.
Something like a friendship graph?
Yeah, I can't quite think of the top of my head. But yeah, this is a really good thing to discuss, to think about.
When you 2 vertices have a common neighbor, there is a vertex which is neighbor of all, isn't it?
Not necessarily, sir.
No.
Not necessarily.
Okay.
You need every 2 vertices to have a unique common neighbor for that.
Yes.
Yeah.
Yeah, even I was thinking about the wheel graph, something similar in lines, but it cannot happen here.
So it's helpful to remember that the Saxo graph is vertex transitive in this case. So it's the same from every vertex.
So basically, when you're saying that it has a triangle, if you take any 3 points from your omega set, 2 of them will form a basis. Right?
No, not necessarily. You could have 3. No. I see. No, there could be 3 that no 2 of which form a base. All I'm saying is that given any 2, somewhere in the graph, there's a third that's connected to both, adjacent to both.
Yeah, but you join 2 points if they form a base, right?
That's right.
So if you're saying that it has a triangle, then that means that there is a 3-element set such that any two of them form a base.
That's
Isn't that
exactly
true?
it. That's
Yeah.
exactly what I'm saying. The in particular line in this conjecture is just the line above applied to the special case where I'm going to take two vertices that are adjacent, right?
Yes.
You know, there are two, and then I'm applying the line before saying they have a common neighbor, so we've got a triangle. That's all that's going on there.
I think there are no further questions. So on behalf of the entire organizing committee, I would like to thank Scott for that wonderful presentation. The next session is on 7th July by Professor Vinayak Joshi. He'll be talking on graphs associated with algebraic structures. So see you all then. Thank you very much.